In this video, we're going to take a look at the electrophilic addition mechanism. So first, before we get into this particular mechanism, we first need to define what is an electrophile. An electrophile is essentially the opposite of a nucleophile. So it's an electron deficient species. It could either be something that's positively charged, or it is the positive end of a dipole. And so it's attracted to regions of relative high electron density, and it will accept a pair of electrons to form a coordinate covalent bond. So it is also called a Lewis acid. So a Lewis acid will accept a pair of electrons, and it's an electrophile. You can use all of those terms interchangeably. So an example might be HBr. And so in HBr, the positive end of the dipole, so the H end, is our electrophilic end. Or NO2 plus, because it has the positive charge, that's also considered to be an electrophile. Now, if you recall, alkenes contain a carbon-carbon double bond that is electron rich. And so it's electron rich because of this pi bond here. And so the high density of electrons in that double bond means that that bond itself is more susceptible to electrophilic attack. So how does this happen? We're going to see a couple of examples of slight variations on the electrophilic addition mechanism, but generally what happens is this mechanism happens in two steps. The first step is the electrons in the pi bond are going to come and attack the electrophile. So essentially, the pi bond or the pi electrons are acting like a nucleophile, and they are attacking the electrophile. And so that's going to create a carbon electrophile single bond, and it's going to leave a positively charged carbocation ion left over. Now, the positive charge is going to go on the more substituted carbon, and we'll see an example of that in one of the mechanisms we show in a minute. Once we've done that, the nucleophile is then going to come in and attack the carbocation. So that's going to come in, attack that, and create another bond between the carbon and the nucleophile itself. So generally that's what's happening. It's happening in two steps, but we're going to look at some specific examples of reactions that we've seen so far in various other videos and see how this works. So let's start with the electrophilic addition of hydrogen halides to alkenes. So this example here, we've got but1-ene, which I've just drawn below, and that's going to react with hydrogen iodide. Now, hydrogen iodide, the hydrogen is a partial positive and the iodine is a partial negative charge. So we do want to show those partial charges. And then we want to show the double bond attacking the hydrogen end of this molecule. So that is going to, in our first step, create our carbocation ion, where the positive charge is going on the more substituted carbon. So that's that second carbon there. So we're going to put the H's there, we'll put the positive there, and then we are going to, maybe in a different color here, come and show the bond to the hydrogen that we've formed. The other thing we're missing here is that when we get attack to the H, it's going to break the HI bond. So the electron pair between the hydrogen and the iodide is going to then go onto the iodine. All right. By doing that, we've generated a nucleophile. So we have a lone pair of electrons on this iodine, and that is now going to attack the positively charged carbocation center, and that is going to produce our final products. So we've got our CHH, we got this. I'm going to leave it sort of written the same kind of way just so we can see where things are. And then in red, I will put our two new atoms here. Okay? Now, how do you know which carbocation is formed? Well, the carbocation is formed when the pi bond is broken, is the one that has its positive charge on the most substituted carbon. And that's because tertiary carbocations have greater stability than primary carbocations. So a tertiary carbocation is the most stable, and a primary one is the least stable. So when you're trying to figure out which one to draw, you're going to look at which one is more highly substituted, and that is where the positive charge goes. The second variation on this mechanism is if we look at the reactions of electrophilic addition of halogens to alkenes. So we've got propene here reacting with bromine. Now, bromine itself doesn't have a dipole, but as it approaches this carbon-carbon double bond, it's an area of high negative sort of charge. Not negative charge, but like high electron density. It will induce a dipole. So we'll get the same sort of attack here. And that's going to create our carbocation. And that's carbocation is going to happen on the more substituted carbon, so the one down at the bottom. And then we are creating a carbon-bromine bond here. And I always forget to do this. This bond's breaking and the electrons are going there. And so we created a bromide ion. We need to show the lone pair of electrons on it. And then in step 2, it's going to attack that positive center to create our final product. I'm going to run out of room here, but that's all right. We'll see if we can squish it in. Okay, here we go. And then we have our dibromo substituted propene. All right, so kind of the same thing in terms of what we've seen, just a slight different flavor. Finally, our last one, you can have interhalogens. So these are a little bit weird, but you can have things like bromine and chlorine together, bonded together. And so the mechanism works the same way. You just have to look at which halogen has the more or is more electronegative than the other one. So if we've got ethene and then we've got bromine and chlorine, chlorine's more electronegative, so that's going to take the negative charge and the bromine will be positive. So we get attack here. That bond breaks. Then we're going to form, this one doesn't really matter where because it's both substituted kind of the same. So we'll put the positive charge on the bottom. And then let's put that in red. That's our bromine. And then we've also generated a chloride ion. We're showing the lone pair of electrons attack to the positive, and that is going to form our final product here. All right, so then we get a bromine on one and a chlorine on the other. So those are 3 examples of different sort of flavors of electrophilic addition reactions. That's it for this video. We'll see you in the next one.